This conference will now be recorded.
Hello everyone. Today we will continue enantiomers, and after we see the features of enantiomer, next we will go to specific rotation and optical rotation that is important for to understand enantiomers. Then we will also see what is enantiomeric excess, optical purity, and RS nomenclature. That is different steps for doing RS nomenclature. That also we will see. So enantiomers, what is enantiomers, that we have to know first. When a molecule possessing chiral carbon. Now what is chiral carbon? What is superimposable mirror image? What is non-superimposable mirror image? Everything we have discussed in the last class, right? So when there is a chiral carbon, and not just chiral carbon, it has to have some non-superimposable mirror image. Then only we can say that the molecule is chiral molecule or asymmetric molecule. And the property which we are getting because of this presence of chiral carbon and non-superimposable mirror image, that property is called chirality. Fine. So these are the criteria. If it is present, then only we can call the molecules as enantiomers. So here you can see a picture. One molecule we have taken, which is having total 4 carbon. Total 4 carbon, as you can see, number 1, 2, 3 and 4. Now at 2 position we have OH group. So without considering any chiral carbon or stereochemistry, the simple name will be butan 2-ol, or you can also call it 2-butanol. But see, here we have a plus sign given. Now if there is a mirror, and if you take the mirror image of this molecule, then you will see 1, 2, 3, 4. Now you will get this type of picture. Now the molecule, which is the first one, and the second one, which is mirror image of this molecule, if you try to superimpose these two pictures, that is these two images, you will not be able to do so. So not just there is a presence of chiral carbon, this number 2 carbon is basically the chiral carbon. So it is true there is a chiral carbon present, but second condition, that is the presence of non-superimposable mirror image, that condition also must be fulfilled. So here, if you rotate the second molecule by 180 degree, suppose you are rotating this molecule 180 degree, now what will happen? You will get something like this, right? Now if you are trying to superimpose this with the first image, you will not be able to do so. Fine. So after rotating 180 degree, what we are trying to do? We are trying to superimpose with the first picture, but we will see that it is not possible. So that is why here we have chiral carbon and also we have non-superimposable mirror image. So that is why this molecule will be chiral carbon. Now what is this sign here that we have just before the name? We have plus sign within first bracket. We have minus sign again within first bracket for the second molecule. So what is the difference between these two? That we'll see. Now before going to that, this same molecule we can also draw it in a different way. So this molecule, if you consider this chiral center as C star, with this C star we have one methyl group, right? We have one ethyl group, that is C2H5. We have one hydrogen and we have one OH, right? Now whether you draw it in this way or in this way, it doesn't matter. After all, it is the same thing. So here both ways, that is two different ways it is shown, so that you can learn to draw a chiral molecule in a different way. So in the first picture, here the methyl group and ethyl group, they are on the plane of the paper. As you can see, they are on the plane of the paper, right? But in the second case, we have written it in a different way. Now the ethyl group, it is as if towards us, and the methyl group, which is away from us, that is behind the screen or behind the paper. And in this case, the CH bond and COH bond, that is directly on the paper. So another way also the molecule can be drawn. But this plus sign and minus sign, that is actually because of the rotation. We will come to that point later. First, we are just trying to see how to take the mirror image. So here again, we have taken this mirror image. This is M for mirror. So after taking the mirror image, we will get the second picture. Now if we rotate it 180 degree, what will happen? Now the COH bond that will be towards right hand side. Okay, and the C2H5 now they will be below the plane, and CH it is on the plane of the screen or on the plane of the paper. It is still that, but methyl which is away from us or behind the paper or behind the screen, now it is towards us. So after rotating this 180 degree, now this COH it is still in the right hand side direction. So at a first glance it seems that you can superimpose this third one, that is after rotating 180 degree of this mirror image. Suppose this is 1, this is 2 and this is 3. So 1 and 2, these two are mirror image, but now we have rotated 180 degree on the molecule 2, you are now getting 3. At a first glance, it seems 3 and 1 you can superimpose. But see, you can superimpose this part or this part. But this part you cannot superimpose, right? Because now towards us, there will be methyl group. But away from us, there will be C2H5. So 1 and 3, you cannot superimpose, right? So in this way, we can understand how to that is the mirror image, whether it is superimposable or not, that you can check in this way after rotating 180 degree on the mirror image molecule. Now a 50-50 mixture of enantiomers. So when I am saying enantiomers, basically what I am trying to say, these two mirror images, they will be mirror image to each other, that is this molecule and 2. So 1 and 2, these two are mirror image to each other. So one molecule will be R, another one will be S. Remember, it is possible only when there is one chiral center. So we are starting this discussion with a simple molecule where you will have only one chiral center, but that is not necessary. The more we will proceed, we will also see example of molecules where more than one chiral center may also present. But right now we will see the simple structure where we will deal with only one chiral center. So when you have one chiral center, one enantiomer will be R, another enantiomer will be S, and that is mentioned basically in the nomenclature. So see here the nomenclature, we have written butan 2-ol, but we have not written RS. We have written something else, plus sign, minus sign. But you can also write R and S, and how to understand which enantiomer is R, which one is S, we'll come to that rules to decide R and S nomenclature later. But these two enantiomers, when there is one chiral center, there will be one R isomer, another one will be S. And if there is 50-50 mixture, suppose you have 1 and 2, these two enantiomers in 50%, 50%. So that is why it is 50:50 mixture of these two isomers. So what will happen? There will be no observable optical activity. And this type of mixtures, we will call it racemate. So what will happen here? Suppose we have already seen how to these chiral molecules, they can rotate the plane of polarized light in the last class. So suppose the first molecule, it is rotating by x degree and towards a particular direction, suppose towards right hand side. Now the mirror image of this molecule, that is the enantiomer of this molecule, which is basically number 2. This will also rotate x degree, but their direction will be opposite to each other. If one is rotating left hand side, that is clockwise direction, another will rotate it to anti-clockwise direction. Or one direction we can call plus direction, another direction we can call minus direction. Okay, so that is the numerical value will be same for their rotation. Suppose 15 degree is the rotation, but their sign will not be same. So when this is happening, that is both the enantiomers are present 50:50, 1:1 ratio, and they will rotate towards a different direction but to the same amount. So ultimately what will happen, one will nullify the other's rotation, and overall there will be no observable optical purity. But suppose somehow it is not 1:1. This 1 and 2, these two enantiomers, if their ratio is somehow it is 40:60. Now in this case, you cannot call it racemate or plus minus mixture, because now one isomer is slightly excess. Okay, so when there is some excess of one of the enantiomer, there will be this type of cancellation of rotation is not possible, and then they will show optical activity. But if it is 1:1 mixture, they will be called racemic mixture or racemate, and they are designated as plus minus. And if it is purely only one enantiomer, it will be either plus or minus. Suppose there is only this one, then you will represent it like this. But if 1:1 mixture is present, you will represent it plus minus within first bracket. Okay. All the chirality centers in the enantiomers are inverted. Suppose there is more than one chiral center, it may happen. So when there is more than one chiral center, and if you are considering its enantiomer, or you can say you are considering its mirror image, then all the R will be changed to S and all the S will be changed to R. So suppose there is total 3 chiral center in any molecule, and there is total 3 carbon chiral center. C star I am writing, and it may be C1, C2, C3. So suppose for C1 it is R, for C2 it is R, for C3 it is S. Now when you will take its mirror image, what will happen? C1 will now be S, C2 will now be S, and C3 will now be R. So that is mentioned in the last point, that all the chirality centers in the enantiomers are inverted. Every R is now S, every S is now R. Okay, that is the property of any enantiomer. Optical rotation. So we have seen what is plane polarized light, and when there is a chiral molecule, they can rotate this plane of this plane polarized light. Now what is optical rotation? We will see its definition. Optical rotation is the rotation of plane polarized light when a light beam is directed through chiral compounds. So light beam, when it is passing through chiral compounds, these chiral compounds have the capacity to rotate the plane polarized light, and there will be some rotation, and we call this optical rotation. We use a special instrument for this optical rotation, which is called polarimeter. And in polarimeter, a plane polarized light beam is directed through a sample, and the sample is taken in a particular tube, and in that tube there will be solution of this compound. So compound will be dissolved in some suitable solvent, and that will be taken in the tube. Fine. And through this tube we will pass this plane polarized light beam. After this passing of this light beam, we will record the rotation of this light beam, that will be measured. Now here you can see some equation. In the left hand side we have alpha within third bracket, and this is actually the observed rotation. This small t, as you can see, superscript, and there is lambda mentioned as subscript. Lambda is basically the wavelength of the emitted light that we have used. So this optical observed rotation, or you can say optical rotation. Observed rotation means the rotation that you are measuring, that is the experimental value. Whatever rotation you are seeing in the polarimeter, that is actually the observed rotation, and that is also the optical rotation. So this is dependent on temperature and wavelength. So we will fix this temperature and wavelength. So that is why which wavelength you have used, that will be mentioned in this way. Sometimes you will see capital D is written. So capital D is basically sodium vapor lamp. That is, there is a specific wavelength which is used in most of the cases in polarimeter during optical rotation measurement. But better you express it with lambda, so that it is a more general form. But mostly the sodium lamp is used, which is having specific lambda, that is wavelength value. So wavelength of the emitted light, that is mentioned in this way, and alpha is the observed rotation in degrees. Basically, what I have said, that this is observed rotation, but it is better to say that the right hand side, the alpha that you are seeing, and that is divided by C and L, this alpha is actually the observed rotation. Okay. Now, if C and L, these two are unity, that means if these two are 1, now alpha is divided by 1 is 1 into 1. That means in that case, these two values will be same. but that is specific case. We will come to that point later. Right now we will just see that this is observed rotation in degrees, then C is the concentration in gram per ml. So be very careful here. Concentration is mentioned only in this unit, gram per ml. Don't use any other concentration unit, not molarity or molarity. L is the path length of the tube that we are using in the polarimeter. So this is the length to which the light will pass. So this is the path length which is measured in decimeter, dm. Okay. So when you have any specific concentration, any value of concentration, any path length, and then you are seeing this value in the polarimeter, then you will divide this observed rotation with C and L. Then whatever you will put it in this equation, and after dividing it by concentration of the solution, path length of the tube, whatever final value we will get, that we will call it as optical rotation. Okay. So it is measured using polarimeter where a plane polarized light beam is detected through a sample and the rotation of the light beam is measured. Now this final measurement depends on several factors. Obviously the concentration of the sample. This is actually the optical rotation, not observed. Observed is this one. So observed rotation we are dividing by concentration in gram per ml and path length which is measured in decimeter, then we are getting the optical rotation. So this final measurement depends on several factors. Obviously, concentration is the factor. If you change the concentration, the left-hand side alpha value will change. Then what type of wavelength of the light you have used, that is important. What temperature you have done the experiment. So everything we have to know because optical rotation is dependent on all these things. Right? Now here, if we take C as 1. Suppose it is 1 gram per ml and L value is also 1 decimeter. This is 1 gram per ml and this is 1 decimeter. Now what will happen? These two will be same, isn't it? Now this is basically the specific case where you have converted the concentration and path length to unity, and under that specific condition we are getting this type of relationship. Now we will use a separate term for this particular condition. Which particular condition? When path length is unity and C is also unity, then the rotation that you are observing, that is called a separate term we will now use. So this is basically specific rotation where C and L, these two are one. So these two will be now same. Now try to understand the difference between specific rotation and optical rotation. Optical rotation that we have seen in the previous slide, that is basically you can do at any concentration or any L. You can have different types of observed rotation depending on what type of concentration you have taken. Suppose in the first record you have taken 2 gram per ml or 0.5 gram per ml. So these two specific cases you will get different types of observed rotation. So optical rotation, this value, it is not fixed, but when it is specific rotation, these C and L, these two are already unity. So we have fixed it to 1. So that is why optical rotation, you cannot see it is intrinsic property of a particular substance, particular molecule. But specific rotation is basically intrinsic property of a certain substance. It will not change because we have already fixed the concentration 1 and L to 1. Obtained by standard measurement of optical rotation for that substance. So when optical rotation is measured, but C and L both are 1, then it is specific rotation. So it gives, that is specific rotation gives the change in the direction of plane polarized light per unit distance, because now L is 1 per unit distance of cell, that is the tube, and per unit concentration of the sample. So C is also 1 gram per ml. So when you are maintaining this condition, under that specific condition, the rotation that we are observing, that is called specific rotation, and it is intrinsic property. Intrinsic property means, suppose when we talk about physical property of any particular compound or molecule. For example, we talk about melting point of a molecule. There is some data, right? you find in some books or notes, that is melting point of this molecule, boiling point of this molecule, density of this molecule, it cannot be changed. These values are always fixed. That means they are intrinsic property. So just like melting point, boiling point, density, this specific rotation is also intrinsic property for a particular compound. So you can have some database for a specific rotation of different chiral molecules. So specific rotation is characteristic of a compound. So just to understand to get idea about the characteristic of a particular compound, specific rotation is important component, not optical rotation, because optical rotation is dependent on so many things. But specific rotation, we have now fixed the concentration on L to already L. So that is, it is more intrinsic compared to optical. So it is characteristic of a compound, just like we check melting point or boiling point of a compound. So when we say that a compound X, its melting point, suppose I am saying 100 degrees centigrade, that means it will always have 100 degrees centigrade. It will not change, right? It is fixed. So just like that, when we talk about specific rotation, it is characteristic, intrinsic property, much like melting point or boiling point. So it is a physical property, you can say, and you can find it in reference books. That is, you can find it in any database type of thing, just like melting point, boiling point, density. So here we will try to understand with this specific example. So see here, it is mentioned that alpha within third bracket 25. 25 means temperature is 25 degrees centigrade. And D means, as I have said, it is sodium lamp. So that is why, that means that specific wavelength we are using for measurement of rotation. So here it is mentioned as plus 15.42. So what this expression actually means? This expression indicates that the experiment was run at 25 degrees centigrade. When the experiment was performed, temperature is 25 degrees centigrade. It is also performed with D line of a sodium lamp. That means sodium vapor is used, which is having a specific wavelength. We know plane polarized light, there is a specific wavelength, right? You just cannot use any light. It has to be plane polarized light. So lambda value is, it is mentioned 589.6 nanometer, and the sample is containing 1 gram per ml of the optically active substance. That means concentration is 1 gram per ml and the length of the tube is 1 decimeter. So when you are maintaining all these conditions, 25 degrees centigrade, you are using sodium D-line lamp, you are using concentration 1 gram per ml and 1 decimeter tube. After maintaining all this, we are getting rotation of 15.42 degree in a clockwise. So when it is clockwise, it is positive. When it is not clockwise, that means when it is anti-clockwise, then it will be negative. So it is clockwise. So that is why we have mentioned it with plus. So similarly, suppose you have taken the same compound, but now you have taken its enantiomer. What will happen? Now similarly, you can say, when you maintain all the conditions just like before, it will have same rotation, that is same degree, but sign will be now reversed. Because if this enantiomer is rotating clockwise, then the rotation of plane polarized light for its enantiomer, now it will be opposite. It will be negative. Now one point it can arise in your mind that in the last slide we have seen that when we take mirror image, R is changed to S is changed to R, like this. So is there any correlation between this positive sign and negative sign, this clockwise and anti-clockwise rotation of plane polarized light, and R and S? So if this question is arising in your mind, we will also come to that point. But before that, we will see what is optical purity and what is enantiomeric purity. Both are actually, they explain the same thing, but sometimes we use optical purity terms, sometimes we use enantiomeric purity, but actually they mean the same thing. So optical purity, it is a comparison of the observed rotation of a mixture of unknown stereochemistry. So suppose you have a mixture of more than one compound and you do not know its stereochemistry. That means you do not know whether it is R or S isomer, which enantiomer is present, what is their percentage. You don't know nothing about it. It is simply a mixture. You only know there is some unknown stereochemistry. There is some compounds with unknown stereochemistry. So when you have this type of sample and you are observing its rotation, okay, then versus the specific rotation of a sample of pure enantiomer. So what this ratio means, first of all, we will take the rotation of the mixture and we'll also take the rotation of the pure enantiomer. And now you are taking the ratio of these two. So what will happen when this ratio is multiplied by 100, we get percentage of optical purity. And that is in this way we can identify the optical purity of the sample. So suppose these two values are given, you can easily take their ratio and multiply it by 100, you get the value of optical purity. It is basically equal to percentage excess of the major enantiomer over the minor enantiomer. So suppose we have two enantiomer, one is E, another one is E prime. Now if these two are present 50%, 50%, then it is racemic mixture. And in that case, it will be zero rotation because one will cancel, because one will rotate, suppose one is rotating plus 50 degree, another one is rotating minus 50 degree. So these two will cancel each other. Ultimately, the observed rotation will be 0 degree. There is no question of optical purity. It is 0. But suppose E is present 40%, another one is present 60%. In that case, you cannot say that it is racemic mixture because now there is major enantiomer, there is minor enantiomer. Which one is major enantiomer? Obviously, E prime is sorry, E prime is the major enantiomer and E is minor enantiomer because it is present in less amount. Now what will happen? This 40% and 60%, if we say it in terms of some example, here you can see we have 2 bromobutane. This is 1, 2, 3, 4. 2 position there is bromine. So if bromine is above the plane, obviously hydrogen will be below the plane. And for this enantiomer, it will be opposite. Now at 2 position, it is again chiral center, but bromine is below the plane. And if it is the case, then hydrogen will be above the plane like this. Now, if both are basically 2 bromobutane, there is no problem in that. But one will be R, another one will be S. How to decide R and S? We will come to that point later because there are some specific rules. We have to discuss it separately. But look at this value of specific rotation. It is minus 23.1. And as I have said, when you have pure enantiomer, suppose this is E and this one is E prime. If it is having some particular value with a negative sign, then its enantiomer will be having the same numerical value, but sign is changed. But don't think that here R is mentioned and here negative sign is mentioned. That means anti-clockwise. So R is always associated with negative sign. S is always associated with positive side. No, there is no such correlation. We'll come to that point in the next slide. So just try to understand this fact that when you have pure enantiomer, E and E prime, if one is having any particular value, rotation it is showing, specific rotation with a negative sign, then for its enantiomer, obviously in pure enantiomer I am talking about, it will have the same numerical value rotation, but now the sign is opposite. So if one is rotating the plane polarized right in clockwise direction, another enantiomer will rotate it to the anti-clockwise direction. Now we'll try to see what is this percentage excess of the major enantiomer. Suppose one enantiomer, that is S enantiomer, we have 20%. So S we have 20% and R we have 80%. So total is 100%. Now what will happen here? This 20% of S, it will compensate the rotation of another 20% of R. That is mentioned in the second picture. As if 20% of S, that is the blue part, it has nullified the 20% of R out of 80%. So if it is so, then 80 minus 20, only 60% of R will be remaining as pure R, isn't it? Because initially it is 80% R, but out of 80%, 20% is already compensated or nullified by the 20% S. So 20% S, it can only nullify 20% of R, not more, not less. So what is the ultimate result we are getting? This 20%, 20%, now their ratio is 1:1. So this part is basically now racemic mixture, and 60% is unaffected, which is excess of R, isn't it? So this racemic mixture, now it is shown with a green color. This blue and red, these two colors are shown as if these two are separate, but as they are compensating each other, so now overall it will be racemic mixture. Only 60% is remaining as pure R, and that will be the percentage excess of the major enantiomer. Okay, in this way we can do. Similarly, suppose take the previous example that I have shown. Suppose 40% of E is present, 60%. So what will happen? 40% of this 60, that will be cancelled by this 40%, and remaining will be only 20% pure. So in this case, optical purity or excess percentage, excess of the major enantiomer over the minor, that is actually this value. We have another term which is mostly used, the term enantiomeric excess, in short E dot E dot. It is equivalent to optical purity and far more often used. So mostly you will see if you have any mixture of two enantiomer, it is in the below it is written as 60% enantiomeric excess or 70% or 98%. 98% enantiomeric excess means it is a very that is a major enantiomer is present in very high amount, isn't it? But lesser is the value of enantiomeric excess. Just like see, in this case it is only 20% enantiomeric excess, and in the previous case it is 60% enantiomeric excess. So obviously its optical purity is higher than this 20%. So you can call it optical purity, but mostly the term enantiomeric excess is used. But after all, they are same thing. More used is enantiomeric excess. Now we will solve this problem and it will be clear to you. Here we have made this question which is saying that the compound is having observed rotation of plus 10.5. Rotation of pure enantiomer is calculated as plus 14. So this is for mixture, but this is for pure. So compared to pure, now it is 10.5. That means some amount of opposite enantiomer is there, which is nullifying some percentage of it. So what we have to calculate? The percentage optical purity of the compound. We have total 3 options, and the last one is saying can't be predicted. So remember, this expression we have already seen, and if we know the specific rotation of a chiral molecule, suppose in this case it is mentioned that pure enantiomer is plus 14. So if we know specific rotation for a chiral molecule, we can easily calculate the ratio of enantiomers present in a mixture of two enantiomers. That is the ratio of E and E prime based on its measured optical activity. So this is basically measured optical activity, that is the experimental observation that you are getting. And this value we will get from database, which is already fixed. As I have said that specific rotation is intrinsic. It is as if the physical property, just like melting point, boiling point density for a particular pure compound. And you can get this value from reference book or any database. So this denominator is fixed, but this value you have to measure it by doing some experimental rotation. So as we already have this information, this will be 10.5 and this will be 14. So when you take the ratio of these two, you will see it will be equal to almost 75%. So in this way we can solve this problem. So 75% optical purity means what? On out of 100, only 75% is the major enantiomer, and the rest of the 25% that is remaining, in this 25%, half of this, that is half of this 25% is R, another half will be S, or if it is plus, another will be, I'm just saying arbitrarily because there is no direct correlation between R and RS and plus minus. So if one is rotating clockwise, another one is rotating anti-clockwise. So out of 25%, half of 25, that means 25 divided by 2, this percentage, 12.5%, that is basically one enantiomer, another 12.5 is another enantiomer. So they are nullifying each other, and as a result, they are now making 25% racemic mixture, and rest of the portion, that is 100 minus 25, that is basically the pure part. Just look at the previous slide. Here, as if you are saying 60% is the pure. So the problem that we have solved, this 60% is now in our case, that is in the problem given, it is 75. Now we will solve another problem using the same formula, but now it is to some extent different. Don't be confused between these two. Read the question carefully. It is saying that optically pure compound X gave plus 20 degree. So this is for pure, not that you can find it from database. And a mixture of X and its enantiomer Y, that is giving us plus 10. So this value is for mixture. Remember in the last case we have for mixture something value 10.5. Just have a look, 10.5, yes. And for the pure it is 14. So here it is slightly different. It is 10 degree for the mixture and 20 for the pure part. Not pure part, I mean the pure enantiomer X. So one is named as X, another one named as Y. So same type of information, just like the previous problem, but here it is asking finally something else. It is asking the ratio of X and Y. That means if one enantiomer is E, another one is E prime, it is simply asking the ratio of these two, whether it is 1:1, 2:1, like this. In the previous problem, same information is given, but ultimately it is asking the optical purity, which you can directly get from by taking the ratio and multiplying it by 100. But in this case, it is not so direct. It is asking the ratio of X and Y. It is not asking the optical purity. So how we will solve this problem? Now, as it is mentioned that for X, it is 20 degree. So this information is given. So what we will do? Suppose X is present with the percentage small x. So small x percentage, that is for the compound X. Okay, that means 100 minus X percentage, that will be for Y, isn't it? Now if X is having plus 20 degree rotation when Y is pure, so when X is pure, it is having rotation plus 20 degree. When Y is pure, it will have rotation again 20 degree, but now it is negative, isn't it? Now we will do the ultimate calculation. Here X into Y, sorry, X into 20. This 20 is basically this value, plus 20, plus, and this is basically the percentage, 100 minus X multiplied by minus 20 degree. So I'm putting here a degree so that you can understand what it actually means. So plus 20 degree, which is for this value, that is for pure X, and minus 20 degree, which is this one, that is for Y. So this is the percentage of Y, this is the percentage of capital X, this is capital Y. Okay. So why we are writing it in this way? Because we know this 20 degree, it is for x, and that value, that is this rotation we are getting, because x is the percentage. So obviously from the remaining percentage, which is for y, and just like we have multiplied x with plus 20 degree, in this case we will multiply with minus 20 degree. Now divide this whole thing by 100. So when you are doing so, because we have considered the total mixture as 100, out of 100, x is the percentage. This is basically percentage of capital X, and this is the percentage of capital Y compound. Okay, so you have to divide it by 100, and ultimately this is equal to 10. So this 10 degree is basically for the mixture, because ultimately this whole quantity is mixture, right? Now we will do the calculation. It is 20x minus, there will be minus 100 into 20, plus 20x, negative, negative, positive, and this 110, it will be 1000. Now it is easy to do. It is 40x equal to, so x will be equal to 75%. Now if x is 75%, which is basically this 3000 by 40, 300 by 4 is 75. Okay, now if this is so, that is x is 75%, so obviously this is the percentage of, let me use different color. So this is the percentage of capital X. So 25%, that must be the percentage of capital Y. Now we need the ratio of capital X and Y, which is basically 75 is to 25. Ultimately it is 3:1. Okay. So this capital X, Y, you can also write it like this, that is X, that is here it is, I have done it in terms of 100. You can also do the same type of calculation by taking the percentage in terms of x and 1 minus x. But in that case, you don't have to divide it by 100. Same result you will get. But if you are considering x as percentage, then you have to divide this whole quantity with 100. But if you are doing it as x and 1 minus x rather than 100 minus x, you don't have to divide it 100. But ultimately you will get this result, which is 3:1. Option C is the correct answer. So same type of information given in both the problems, but in the previous problem it is basically asking the percentage optical purity, when that you can easily get by putting in this expression, but here it is asking something different. Okay. And if you are asking, if your one question is also arising, what will be the optical purity in this case? Now that also we can calculate. See, here 75, that is the percentage of one enantiomer, which is 6. And its enantiomer Y, that is 25. That means when we have this type of mixture, 25% of Y, it will nullify 25 out of 75. So the remaining part, that is 25, is already lost by this 25 of Y. So when you are taking the rest of the part, it is basically 50. So this will be the optical purity. And just use the previous expression, that is mixture optical specific rotation of the mixture divided by specific rotation of the pure compound. Then 10 divided by 20 into 100, that is basically 50%, isn't it? So once you know the ratio of x and y, you can also find the value of optical purity, which you can also get by directly putting in the expression of optical purity. So in this way, we can get the correct answer, option C. Now we will discuss this important information that you have to know. That is, there is no correlation between the positive and negative sign in the specific rotation. So there is no correlation between RS nomenclature. So there are some specific rules based on which we can decide what is the, whether it is R configuration or S configuration, and according to that Just before the IUPAC name, we put R or S for that particular compound. But this RS nomenclature or configuration, it has nothing to do with this plus or minus. We already know, in the last class we have seen the positive sign, which is clockwise. When it is so, it is basically denoted by small d. When it is negative, it is denoted by L. Remember, levorotatory, dextrorotatory, these two terms we have seen in the last class. So D is basically associated with plus, small l is associated with negative. And also be careful, don't use capital D or A, capital L. That has completely different meaning in organic chemistry. In this case, when we are talking about rotation, it is basically small d and small l. And it has nothing to do with RS nomenclature. RS notation is basically used for labeling the absolute configuration of chirality center, while these D plus and L minus, they indicate the direction to which the sample is rotating the plane of a polarized light. So when you know that is something is mentioned, like before the name plus is mentioned or negative is mentioned, from this information you can understand whether the compound is rotating the plane polarized light towards clockwise direction or anti-clockwise direction. Okay, but if there is RS notation given, from that notation you can draw the molecule, whether the groups in the chiral center they are present on the plane of the paper or away from us or towards us. But you cannot understand from RS notation what is the direction of plane polarized light. So this RS notation has completely different purpose. These D plus L minus, it is having completely different purpose. Look at this example. This molecule, that is 2-butanol, these two, they are basically enantiomer to each other. And here one form is mentioned as R, another one is S. How to do it? We will discuss that. But look at the value of this specific rotation. It is negative 13.52. It is positive. That means it is rotating. This enantiomer is rotating towards clockwise direction, but the first enantiomer is rotating towards negative direction. So here S is rotating towards plus sign, clockwise direction, and R enantiomer is rotating towards anti-clockwise. Another example, look at this. This molecule is glyceraldehyde. In this molecule, we have just one chiral center. So in this chiral center, you have total 4 different groups: CHO, H, OH, and CH2H. So this is chiral center. In this chiral center, it is having S configuration, but it is negative. Though it is S, but still it is rotating anti-clockwise. That means I am trying to say, just because it is S, some molecule is S, that does not mean it will be having positive sign or negative sign, because sometimes it may be positive, sometimes it may not be positive. That you can see from these two examples. And for its another molecule also say, again S is associated with plus sign. So S can be associated with negative sign, S can be associated with positive sign, it doesn't matter. Similarly, R can be associated with negative or positive, both. So don't think there is any correlation. That is the important point to understand. There is no simple way to predict the direction of rotation based on structure. So suppose this type of structure when given, you can understand based on some rules whether it will be R or S, but you cannot understand whether this is negative or positive. If you want to know whether it is negative or positive for any particular chiral molecule, you will have only one option, and that option is, if you want to know the direction of a molecule that rotating the plane polarized light, you just have to measure it with some polarimeter. There is no direct method, but RS nomenclature or notation, that is basically used for absolute configuration of chiral center, which you can do if you know, suppose you know which group is below the plane, which group is above the plane, which group is directly on the plane of the paper. If these informations are available, you can decide R or S. You don't have to do any experiment. But if you want to know the rotation of the plane polarized light done by this molecule, you have to do the experiment. Then only you can write negative sign before its name or positive sign before its name. Now we will solve this. Out of the following, it is asking the alkene that exhibits optical isomerism. So all are basically alkene, isn't it? It is ending with "in". So we'll draw the structure of this one by one. Number 1 is 2-methyl-2-pentene. So 2-methyl-2-pentene. At 2 position there is double bond, and 2 position there is also methyl. Next, first let me draw all the pictures. 3-methyl-2-pentene. So again 2-pentene. But now at 3 position we have methyl. Okay. Number 3, 4-methyl-1-pentene. So this is 1-pentene. 4-methyl. 4 position there is methyl group. Last compound, 3-methyl. This is 3-methyl-1-pentene. Now the question is asking which one will exhibit optical isomerism. It is not asking cis trans or any geometrical isomerism. It is simply asking optical isomerism. So to understand optical isomerism, we just have to check whether there is any chiral center or not. So the first molecule, here we do not have any chiral center, that is any sp3 carbon where 4 different groups are there. If you consider these 2 carbon, obviously here we have 3 hydrogen attached to carbon. This is also a carbon where 2 hydrogens are present, so this is not our answer. In the second molecule, here also we do not have any chiral center. Third molecule, now if you are thinking this center, that is a 4, if it is not chiral center because 2 similar groups are present, right? Now the last one, here this center is having methyl group, ethyl group, this vinyl group, and also there is hydrogen. 4 different groups are present. That means this should show optical isomerism. Next question, which of the following molecules doesn't show stereoisomerism? Now it is asking doesn't show stereoisomerism. Now when we are talking about stereoisomerism, you have to consider both optical as well as geometrical. Not just GI, you also have to consider optical isomer, both. So one by one we will draw the molecule. 3,4-dimethyl hex 3-ene. So this is hex 3-ene. 1, 2, 3, 4, 5, 6. 3 position there is double bond. Now at 3 position there is methyl group, and at 4 position there is methyl group. So is there any that is stereoisomerism possible or not? Here stereoisomerism possible, but which one? Here GI is possible, isn't it? Because we have ethyl group and methyl group, and if these 2 ethyl group, that is these 2 ethyl group as I have drawn here, they are opposite to each other, so it should be trans. You can also draw the cis. So this is not our answer because we have to find does not show. Next molecule, 2-methyl hex 1-ene. So now at 1 position we have ene, and at 3 position we have methyl groups. Now GI is not possible because we have 2 same groups. But this part, if you consider this carbon 3, here we have 1 hydrogen is also there. We have 1 methyl, propyl, this total group, vinyl and hydrogen. So this is also showing some optical isomerism. This is not our answer. Last one, sorry, third one, hex 3-ene. That means 1, 2, 3. 3 position there is double bond. 3 position there is also ethyl group. That means 2 ethyl groups here. You cannot have GI. But is there any optical isomerism possible? Optical isomerism here not possible. We do not have any chiral center. But here GI is not possible here. Optical isomerism is not possible. Is it our answer? But we also have to check the last one. The last molecule is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Now at 4 position we have methyl group. That means here this center is chiral. Why? You have methyl, hydrogen, ethyl and this total large group. But here GI is not possible. Only OI is possible. GI not possible because you have 2 same groups. So only in compound 3 you cannot have any GI. Similar groups, no GI possible here. You also do not have any chiral center. So this is the only molecule where you will not be able to get any type of stereoisomer, whether it is GI or OI. In the first case you can get GI, second case you can get OI. Last case also you are getting chiral center Y possible, but only in the third compound you cannot have OI or GI, none of them. And it is stereoisomerism is at least one of them you must have, but you are not getting any of them, so it will be the correct answer. Now the next we will not start it, because next class we will start with the rules to decide whether it is having R configuration or S configuration for a chiral center, particular chiral center. So we will discuss it in the next class. So we are ending the session here. Thank you for listening.